next speaker is Ryan Perkl, professor at University of Arizona and in the College of Architecture, Planning, and Landscape Architecture. And he's going to be talking about conservation planning and geodesign, and that's not the right one. Let me go, how's that? That looks better. And you're on, Ryan.
Excellent.
Thanks.
Thank you. Well, I'd like to start by, again, thanking Jack and the wonderful summit organizers. This is a heck of a show that you folks put on. I also want to start by thanking a number of my research students that without their blood, sweat, and tears, this wouldn't take place. So Kyle Bean, Samuel Chambers, and Garrett Smith were instrumental in some of the new material that you'll see here today. So I want to acknowledge them and thank them for their assistance. So I'm somebody that's interested in how our built systems impact landscape scale processes and impact how wildlife move through our landscapes. This is some work that was recently completed in collaboration with Arizona Department of Game and Fish, where we were set out and tasked to essentially model Arizona's naturalness, i.e. the landscape integrity of the state of Arizona. So this is a summation of our human footprint, a summation of all of the built infrastructure and the projected zones of influence associated with that infrastructure to get an understanding of where those last remaining natural locations throughout the state of Arizona. This is particularly important then because we can extract and identify these last remaining wild places that are essentially void of human infrastructure. This is very important for us as conservation planners because these become candidate sites for conservation efforts, protection efforts, those types of things. We were also tasked then with understanding how the state of Arizona, how the landscape connectedness of the state plays out given this built infrastructure and the structural intactness of this landscape. So we'll get into the details afterwards. You can come and chat about this, and we can talk about how graph theory works really, really nicely for evaluating a large problem like this. But what we're really interested then is through taking an analysis like this to start to construct a conservation blueprint based on landscaped intactness and naturalness through the state of Arizona. This again is something that we're very interested in for conservation planning. What I want to do now then is come into my neck of the woods. This is the city of Tucson with the landscape integrity surface, the human footprint. And I want to transition between this state scale and something that we might start to look at a more local or urban scale analysis. And so the statewide analysis gives us a context of how the natural landscapes around Tucson play within the whole of the state. So this landscape level analysis can then help to inform and prioritize local land use decisions as we expand the city of Marana, as we expand Interstate 10 throughout this area. So what I talk about a lot then is how this statewide analysis can ultimately help to inform local conservation priorities. So one that we're working on right now with the National Park Service in Saguaro National Park West and East is ultimately landscape scale connections between these two portions of the natural park. So for this, we'll use a different connectivity modeling method, and we're actually using a circuit-based approach here to model resistance and transmittance of agents through this landscape, i.e. moving between different portions of the park. We'll see that this was an area that was also prioritized in this state level analysis. So now we're keying into local priorities as well. Now the beauty of geodesign then is that we can take a hypothetical development, we can parameterize that into our initial surfaces, and we can rerun these models to ultimately get an understanding of how that new development would impact this and ultimately change that path of movement between these two areas. We can then simulate urban expansion for the whole Tucson metro, and now all bets are off as far as how we would look at connecting these particular portions of the landscape. So again, this is one of those areas where geodesign becomes instrumental in us understanding how these locally implementable land use decisions are ultimately going to impact these larger landscape processes. So now we're looking just north of Saguaro National Park on the eastern portion, and I want to zoom into this little bottleneck that both the statewide analysis and our local analysis has identified as being a critically important area. So for this, we bring in our integrity surfaces again, and we're essentially again modeling that flow. So you can see that transmittance of those of these random dispersers through this particular area. We'll then bring in the hypothetical new development, and this is just to show this concept, right, and how that chokes off that bottleneck that was critically important. So Then we're into land use planning scenarios. And now let's take and integrate a plausible land use development scenario, persisting this suburbanization, and ultimately get an understanding of how that impacts this projected model flow. Okay, so we've opened it up a little bit, but we still have some work to do there. So let's take another alternative scenario. And at face value, this doesn't look a lot different, but we've ultimately increased components of green infrastructure, reorientated some of the streets to make this portion of the landscape more permeable. And now we're starting to get somewhere. Now we're starting to address this issue of connectivity in this very localized area that also has statewide importance. So the real value in this then is we can vet the impacts from our connectivity models from the multiple scenarios, and through a change detection process then we can evaluate which of the scenarios is most like the benchmark condition, or even better still, which of the scenarios improves landscape connectivity. So this was with that initial hypothetical development, just a single very place, lots of change. This one is not working well with the landscape. But as we make these adjustments, we become more and more similar. And this is what we're looking for in evaluating our land use decision-making process. So once we've identified this flow, then we can conduct an additional landscape connectivity approach. So this is something that most of you may be familiar with, a least cost corridor to link these particular areas. Another thing that my group is interested in is physically populating the interior of these modeled corridors with vegetation designs. And so for that, we're developing this automated design module that I've spoken about previously here, but we've made significant progress on it, so I wanted to bring it back in here. Here what we're doing is essentially creating a library of native vegetation that we may find in the Sonoran Desert. We're parameterizing characteristic surfaces for where this vegetation may or may not be capable of being supported in the landscape. These then capability surfaces can be brought into the GIS. Capability can be converted. Ultimately, cells that aren't capable of supporting a particular species fall out. We can then start to arrange these cells, these capable cells, in various patterns and configurations that are known to help facilitate the movement of wildlife. And because we have many surfaces, we can bring in alternative vegetation types. Through a simple conversion process, then we convert these quantifiable cells into discrete points, and the real beauty of this then is that these discrete points are nothing more than symbols that can then be linked back up with our vegetation library. So in a very robust way, we can start to play with vegetation patterns for increasing vegetation densities, increasing vegetation linearity, and again, this would all be based on the particular wildlife that we're attempting to promote the movement of and promote the habitat suitability for. So as a concept, a traditional model corridor, we're ultimately integrating then these concepts of the landscape design. And so we're developing a tool that will do this for us for very large portions of the landscape very, very quickly. Now, this is a rules-based approach, but there's no shortage of additional information that we can manually bring into this process. So initially modeled corridors, now one populated with capability cells. And what this ultimately translates then into is, this is a scene from ArcScene, where we're actually taking our vegetation library then, and this is a 3D scene of these 3D vegetation models planted in the landscape in cells that are capable of supporting each of these vegetation types. So as we move through these scenes, you can start to see how this could be a really interesting application for restoring very large landscapes based on change that may have occurred there. And then I include this to show that because this is based on a set of rules and pattern generators, we can apply very formal architecture in this or very natural designs and plans in this. So we're working through scenarios. We're ultimately informing the interior design based on these vegetation patterns. And now one of the things that we're particularly interested in is, again, bringing in this interface between the built and natural landscape. And so for that, what we're ultimately looking at is working with platforms like CityEngine that are these parametric model-based platforms established by rules and that work really nicely with these transect development concepts. So here we're taking a traditional urban development transect, which is loosely based on what CityEngine is developed around, and we're applying it to green infrastructure, and ultimately then linking concepts from a green infrastructure transect design into a parametric model to ultimately employ those rules given where that falls with relationship to the green infrastructure. So here, this is our original surface that you'd seen with flow before, and we're starting to construct a CityEngine scene around this. So from that hypothetical land use scenario. In applying the CityEngine scene and applying the transect concept, we can then increase and adjust densities of this buildings in this parametric model based on its relationship to the green infrastructure, right? So we can adjust the intensity and density of development as it comes in contact with these components of green infrastructure. And because of the parametric model, we can apply this really, really quickly and test all sorts of model outputs, and then go back into the connectivity component and again test the impacts, right? So we can then start to bring in the outputs of our automated design module and bring this into CityEngine again and start to actually bring in the planting designs for these particular scenes. This is one particular scenario. Another scenario where we're looking at another bottleneck, again, we're experimenting with density configurations in this parametric model, ultimately bringing in the results of these automated design module outputs to start to derive scenes. These are not randomly placed vegetation. This vegetation is linked to the capabilities of that landscape in that particular point in this particular scene. So this, I think, is really the power of where we can start to go with testing these iterative concepts. We can start with large landscape scale processes, run through multiple scenarios, plug those scenarios into something like CityEngine, and ultimately start to then kick this design back to the beginning of the process and rerun these things to strive towards more perfect solutions in these applications. So with that, again, thank you to my students and thank you all for the time.